You left. Walking in and walking out doesn't mean that you're here. Having your backpack here is not you either. Okay, let's get started. We're going to finish up talking about capacitors and then talk about electric circuit analysis. By the way, just go over because we have a lot of them. I don't see Bridget, Lindsay, Diksha, Austin, or Sade. So, let's continue on where we left off last class period. So, starting with the clicker question. How can you calculate the electric field outside of a flat conductor with a constant charge density? Going to have to try harder, Jared, not just press a button. Okay, so we had 3 and 10. Not a strong showing there. Let's see. Bridget came in. Lindsay came in. Austin came in. And no, Sade didn't. Oh, no, there you are. Okay. Okay, so still don't have Diksha. Okay, this was a question from last class period, just checking our continuity, remembering that with those flat plates, we used Gauss's law. We made a little Gaussian pillbox, one side inside the conductor, one side out. So we have charge on the surface trapped in there. Electric fields are going to be like this. And then we say, okay, let's look on the part of that pillbox that we call it a Gaussian pillbox that's inside the conductor. What's the electric field inside a conductor? 0. So the flux on that end is 0. Now, what direction is the area for the sides of my cylinder? It's what?
I understand your drawing. What is the pillbox?
The pillbox is the imaginary Gaussian surface for using Gauss's law. Anytime you use Gauss's law, you have to have the imaginary Gaussian surface. So what direction would the area be on a surface here? What Tori said on the side here. On the side here, what direction is the area pointing? Out. And so my area is like that on the side. Well, what's the angle between the area and the electric field on the side there then? 9 degrees. And so how much electric field is going through the side? 0. Hence the flux on the sides is 0. And so we're left with the entire flux is just the area of the cap times the electric field. And so in that case we have the flux is just equal to the electric field times the area of the cap, and that's equal to the charge enclosed divided by epsilon 0. But charge enclosed is equal to the total charge over the total area times the area of the cap. So I put those together, and I have so I can just cancel the area caps. Oh, I forgot the epsilon 0. So I can now just cancel the areas of the cap, and I have the electric field is equal to the charge over area epsilon 0. So that's how we find the electric field between parallel plate capacitors. Almost did the wrong thing there. So review of the equations we did. The charge is related to the voltage for a capacitor by the capacitance. That's the definition of capacitance. And then using the equation for electric field that we just found and the fact that the voltage difference is equal to electric field times the distance parallel, then we can substitute for the voltage difference from the electric field we just did, and we find that the capacitance has a physical value of epsilon 0, the permittivity of free space, multiplied by the area of the plate and divided by the separation of the plates. A physical calculation. And we went through last class period, the units are farads. Most capacitors we use have very tiny capacitances. So we very often use this, or even this. What's the first one I wrote? Microfarad. The next one? Nanofarad. And the final one? Picofarad. Okay, just making sure we're all up to date on that. Okay, I thought I had removed this slide. I copied the picture onto the next. I thought I'd moved. Wow. Uh-oh. Sometimes I must not save things because I thought I'd remove both those slides. Okay, this clicker question was supposed to be the next stop. When a capacitive computer key is depressed, what happens to the charge on the capacitor if voltage is held constant? This was the last clicker question from last class period, and I put the equations that are relevant right here because I didn't think you'd have it memorized. So when you depress the key, the separation between the plates gets smaller. You're holding a constant voltage across those plates. So if the voltage is constant and the separation gets smaller, what happens to the charge? Okay, we're all in. We had 3, 13, and 2. We had a good majority here that answered the charge increases. So let me ask Jaron, how did you come up with the charge increases?
Because the plates get closer together, then the charge increases.
Why?
Because it does.
I mean, it does. That's the correct answer. But I mean, physics, we don't look for the correct answers. We look for the reasons for the correct answers. Awesome.
You just look at the equation, and if the distance decreases, then the capacitor is going to increase. And then if you put into your charge equation the bigger C, you're going to get a bigger Q.
Okay, so he says if the distance decreases, so if the distance goes down, then the capacitance has to go up. And then we look here, if the capacitance goes up and the voltage stays the same, the charge had to go up. Thank you. That was the perfect answer. Here's another practical example of using capacitance. In a type of microphone, you have two plates, and one of them can move with respect to the other, and you put a constant voltage on them, and when they move in and out, you're going to have the same actions with that key that you will have when it's pushed in. The charge will go up, which means that you will have a spike of current going into it. And when it moves out, the charge goes down, you have a spike of current going out. And so you convert the motion of that little plate into current. And that current is then the signal that we use for recording the sound, amplifying it. Okay, now the idea of dielectrics. As we saw from the lab on the second day of the semester, air can only hold about an electric field strength of 3,000 volts per millimeter. If you have a larger electric field, you're going to have charge travel through the air. You're going to have what we call breakdown. And so if we want to have a capacitor that stores a lot of energy, we're going to need to have probably a pretty high electric field. So how can we make it hold a higher electric field that air can handle? we put something in there that's going to act as a dielectric. And that dielectric allows it to have a larger electric field. And we'll see why in just a moment. So the dielectrics have what we call a dielectric constant kappa. So kappa is the dielectric constant. And that kappa tells us the ratio between the electric field that would have been present and the electric field that's actually there when you have the dielectric in place. So if you look at this, the electric field that's actually between the plates is equal to the electric field you would have had without the dielectric divided by the dielectric constant. Dielectric constants are always greater than or equal to 1. So that means the electric field between the plates is always less than the electric field would have been without the dielectric. And because the electric field depended on kappa, it turns out the capacitance increases proportionally to kappa. So your capacitance has another term if you put a dielectric in it, that kappa, which is the dielectric constant. Well, what causes, actually I think it's cause first. Yeah, let's move past that. That's saying the breakdown voltage is the dielectric strength. So this here is the highest electric field that can be withstood, or that can exist. And so you see something like mica, it can have electric fields approximately 200 times stronger. Well, actually 200 divided by 3. Let's go with 66 times stronger than the electric field that you can have in air. So you can have a much higher electric field in mica, and mica has dielectric constant somewhere between 4.5 and 8, which means that the ratio between the electric field you would have had without it and the one you have with it is that number. Or, put another way, the capacitance, if you use mica as an insulator, is going to be 4.5 to 8 times larger than if you had air separating the plates. So putting that mica in there actually gives you 2 advantages. Advantage number 1, a larger capacitance. Advantage number 2, you can put a higher voltage on the capacitor. Now, if you look at these dielectric constants, air has a dielectric constant that's basically 1. Paraffin, 2. Rubber, something we often think about as a good insulator, it only has a dielectric constant of 3 to 4, and it only increases the dielectric strength by up to 50. Mica is where it's at if you want to do your best job for dielectrics. Now, here's how the dielectrics work, because the dielectrics can be confusing. Dielectrics are called dielectrics because you have something that has positive and negative charge that can be separated to make an induced electric dipole. Now, sometimes they'll actually use dielectrics that have an electric dipole without it being induced. If they use those, then your capacitors actually have a side that they mark as the positive side because the dielectric already has a dipole moment. But if it has no dipole moment, which is what we're showing here, it's unpolarized, you can use the capacitor either direction. When you put charge on it, the positive charges would be attracted to the negative plate, and the negative charges to the positive plate. But then if you look at the electric field that produces, with all of these things made into induced dipoles, I should have just put these 2 pictures on one slide, it acts like you have negative charge on this side and positive charge on this side. So what does that do to the electric field? That's going to make an electric field that points, of course, from positive to negative. So you have an induced electric field because of those induced dipoles that's opposite the external electric field. And of course, if I have 2 electric fields, what do I do to find the total electric field?
Add vectors.
Add those vectors. So I have the external one, the one I created is this direction. Whoops, got to turn around. That direction. And then I have the one that it induced, it's this direction. I add them together, and I have a reduced electric field strength. Because of having, right, so the actual electric field in there is reduced, which was consistent with the equation we saw. The electric field is the electric field we would have had divided by kappa. And so by reducing that electric field strength, you're changing the capacitance. You had a question, Chad?
Yeah, I thought the point of the dielectric was to get rid of air as your capacitor. So why would you have space between?
You wouldn't. This is just for drawing's sake.
Okay. So what is the field then that goes by the dielectric versus the one that goes through it?
Okay, the green one is the field that would have been created if you did not have the dielectric there.
Oh, just between the two plates?
Yeah.
I got you.
And then you have that dielectric there that the way this is shown is it shows it is canceling every other of those field lines. Well, I mean, that's not really what's happening. But it's creating an electric field that's going the opposite direction, so when you add them up, it's smaller. Right, so that's why it shows only every other line here to show, oh, that's a smaller electric field than you have out here. And that's why they have the gaps, so you can compare the two. Tori.
So why is reducing the electric field strength advantageous here?
Okay, why is it advantageous? Number one is that it increases your capacitance. And it's kind of hard to make big capacitors. Like you want to have in your car's audio system, capacitors store energy. If you have a woofer, woofers use enormous amounts of energy. And so you put a big capacitor, like a 1 farad capacitor, in your car's audio system so that you have enough power to drive the woofer without your headlights dimming. Right? Because they would do that. Right? So you put in like a 1 farad capacitor. Well, how do you make a 1 farad capacitor? It either has to be huge or you have to have a really good dielectric. And so you put in that dielectric and you can make it smaller. The second thing is it allows you to put larger voltages on it because it's increasing the dielectric strength. So there's two that work together. Okay, a numerical practice problem. A parallel plate capacitor has plates that are 1 meter squared with a spacing of 0.5 meters. So draw my picture. There's my two plates, and they are area equals 1.00 meters squared, and the spacing is D is equal to 0.500 millimeters. The insulator has a dielectric constant of 4.9. What symbol do I use for that? Kappa, actually. I know you say K because it looks kind of like K. It's the Greek K. And dielectric strength of 18 kilovolts per millimeter. So my first question, what is the capacitance? This is probably not going to challenge you. What's the equation for capacitance? Okay, so I just got to put my numbers in. So that's 4.9 times 8.85 times 10 to the minus 12 coulomb squared per Newton meter squared times my area, 1.00 meters squared, divided by my separation, 5.00 times 10 to the minus 4 meters. And someone with a calculator, what does that give me? Seems like a really small number, right? But capacitances generally are. So that would be 86.7 nanofarads. So we have the capacitance. Now we have the question, what's the maximum charge that can be stored in this capacitor? How do we do that? Okay, we have Q equals C delta V. And we know that we have a maximum electric field that is delta V over D is 18 kilovolts per millimeter. So if I can have 18 kilovolts per millimeter, what is the voltage difference going to be? Okay, she is correct. Since D is 0.500 millimeters times 18 kilovolts per millimeter, that's going to be equal to 9.0. Was there another? Nope. Only two digits here. 9.0 kilovolts. So that means Q is equal to 86.7 nanofarads times 9.0 kilovolts, which is what?
Those are not in nano.
Wait, times 10 to the minus, yeah, you're
I
right.
did them in just there.
Set 7, 8, what?
7.8 times 10 to the minus 4.
Or, yeah. So 780 microcoulombs. Right, so we can do these calculations just using those simple equations. The equations are simple, the ideas are what's more complicated because you can't see what's going on with the capacitor. So you have to have a framework in your mind for visualizing how these things are relating. Any questions about the problem? All right then. Energy stored. At the very beginning when I introduced capacitors, I said their purpose is to store energy in the form of electric field. In fact, we just this week in our family worship, we were reading about the story of Uzzah. You guys know the story of Uzzah? King David wanted to move the Ark of the Covenant from, what is it, Jeroboam's field or something like that, to Jerusalem. And so he had a pair of oxen that were perfectly matched, pulling a brand new cart on which was placed the Ark of the Covenant. And it was going down the road, and everybody's celebrating, and it tipped a little. And so Uzzah reached out and touched it, and what happened? It died, okay? And so, you know, they store it temporarily in something house, and the prophet Nathan tells David, well, if he would have followed God's instructions of having it carried on the shoulder, you know, on rods and shoulders of priests, this wouldn't have happened. It's because you were carrying it the wrong way, and so then the priests carried the rest of the way there, except for Uzzah's death. So there are scientists who say, you know, that the story probably has a germ of truth, but they don't believe in God. And so they say, how can we explain the germ of truth, somebody touching it and getting killed, if there was no God? And the answer that scientists have come up with is that that Ark of the Covenant was essentially a capacitor. We have a name for that type of capacitor, it's a Leighton's jar. But it had gold foil around the outside. and then it had, the golden calf inside. And so you could store up a pretty big charge separation, have a pretty big capacitance for that. And so as it's traveling along, just like when you walk along and drag your feet, you have wind blowing out and whatnot, and it could slowly build up a bigger and bigger charge that is stored. And then when Uzzah touched it, all of that charge goes through his body and kills it. Now, it's all conjecture, but it's kind of interesting to look at how people have tried to take the science involved here to describe a story in the Bible, but it takes away some of the action of God. Although, honestly, it makes me feel a little better because I never liked the story of a well-meaning person getting killed because he touched it. Didn't know better, thought he was doing good. I don't like that idea. Okay, so storing energy, something capacitors do. We want to be able to calculate that energy. And so if we just connect a battery, and by the way, I have a little battery slide coming up after this just because I named the wrong metal when I talked about batteries before. I have a battery and I connect it up. And what would the charge separation be before I connected the battery up? I have a nice pristine capacitor. That is right. And says 0. So I start with 0 charge. The instant I connect the battery, what's going to happen? Okay? I will have a spike. The charge will start flowing rapidly. But it starts flowing. I don't have an instant charging. It has to take time because the charge has to physically move. So in talking about the work done, we can do a calculation saying, okay, we start with no charge. If I have no charge, then the voltage difference is 0. Because we know that since Q is equal to VC, then V is equal to Q over C. So we start with no charge, we start with no voltage. And so the work done to bring the first electron across is 0. Because you moved a charge of 1 times 1.6 times 10 to the minus 19 coulombs across a voltage difference of 0. But now you have a little bit of charge. So you have a little bit of a voltage difference. And so when you bring the second electron, there is some work that's done because you're now moving it against the voltage difference. And so after the second electron, you have a stronger voltage difference, takes more work. So we can make a graph of that. Please be the next slide. Well, this is the math showing it. We have to add up the charge times the voltage difference for each piece of charge that goes across, which those of you in calculus will recognize is integral of V dq from Q initial equals 0 to our final Q. Now for our calculus people, since V is equal to Q over C, that's equal to the integral from 0 to Q of Q over C dq, what do I get? And my limits are Q to 0. So it's going to be 1/2 Q squared over C. Or since the total V is equal to total Q over C, that's also the same as 1/2 QV. So the total energy stored, with calculus, that was a straightforward calculation. Without calculus, that's covering the rest of you, more than half. What we do instead is make a graph. We make a graph, and on the vertical axis, we put the voltage difference across the plates. The horizontal axis, the charge that's moved. And just like before when we talked about making a graph of the velocity versus time, or the force versus distance, right? Force versus distance, we calculate the work was the area under the curve. Velocity versus time, we calculated that the distance traveled was the area under the curve. Here, it's the energy stored is the area under the curve. And so since this makes a triangle, the area of a triangle is 1/2 base times height. And so that's where we get the equation here without using calculus. What's important here is we now have an equation to tell us how much energy is stored. And so like I said, we can write it multiple ways. U is equal to 1/2 QV is equal to 1 over 2C Q squared. And you can also put it in terms of V, since 1/2 CV squared. This is actually the one that I prefer because most of the places where I use this, that's the equation that's appropriate. So we have those, let me take away my box because they're all equivalent. We have this for calculating the energy stored. There is one more form that we're going to get to in a few weeks, and that is to calculate the electric field. And so what we're going to calculate later on is we're going to take this and we're going to calculate how the energy per unit volume relates to the electric field. But not today. Okay, now changing topics. I talked about the lead acid battery, and I said, well, one plate's lead and the other one I guessed was zinc, because you use zinc and copper. But for a lead acid battery, such as a typical automobile battery, each cell has one plate that is lead and one plate that is lead oxide. So basically they're both lead, but one's oxidized. And you have chemical reactions that occur because of the sulfuric acid that they're sitting in. And so at the anode, at the lead one, you have the lead plus sulfuric acid produces a lead sulfate and a hydrogen ion and these 2 electrons. So if the lead plate becomes negative because that chemical reaction leaves 2 excess electrons after it's done. On the other plate, the cathode, you have the chemical reaction of the lead oxide reacts with the sulfuric acid, also requiring 3 protons and 1 electron. Where's that electron come from? It pulls the electron out of the metal at large, making the metal positive in charge because it took an electron from the metal, an extra electron, to make this reaction. And so the cathode becomes positive, the anode becomes negative, and both of these things start getting eroded away because of your process. But then when you charge the battery, anybody thought about how you charge a battery? You connect something that actually makes current go backward through it. Remember, current's supposed to come out of the positive side, out of the cathode. If you want to charge the battery, you would take this and put a power supply here that has a bigger voltage, positive, compared to this reference point, the negative, and forces current to go the opposite direction. And when you force the current to go the opposite direction, you force the chemical reaction to go in the opposite direction. Most of you have had a chemistry class and you've learned about chemical reactions actually go both ways. And you establish an equilibrium where the rate this way is slower than the rate that way. Until it moves on and you get to equilibrium and it stops when the rates are going the same speed. Well, by putting that voltage, you can make the chemical reaction work more in the reverse direction and rebuild your plates. And so that's how you charge the battery. But of course, you're never going to rebuild the plate to pristine condition. And so over time, your plates get more and more mangled by having material removed and then added back on until they fail. Often you'll have it thin and something breaks off. And so that's how they fail. So I just wanted to make sure I covered that since I said the wrong metal before. And for a lot of students, seeing the chemistry makes them feel comfortable. For me, that's not the most comforting thing in the world. It's not nearly as fun as talking about this stuff. So this stuff. In the lab, we saw resistors in series and parallel. Which one of those is series? Okay, the top one. I asked that question just to make sure we're on the same page, there's no confusion. In series, what has to be the same for the elements? The current is the same for all of them. The lower one is in parallel. What's the same for all of those? The voltage. And then we have over here the idea of the equivalence. Here I have 3 resistors in series, and I can replace it with one equivalent resistor. And in lab, I went through the derivation that told us that the series resistance was just equal to the sum of the resistors. I started thinking about parallel there, as you can tell by what I wrote. And for parallel, it's like this. You might wonder why I do 3 resistors. The reason I do 3 resistors is because oftentimes people see this parallel relation and they take, if you have 2 resistors in parallel, if I invert both sides, I'd have R parallel is equal to 1 divided by 1 over R1 plus 1 over R2. Right? Right? Okay, that's just inverting. Now if I multiply everything on the right side by R1, R2, I get that, and we see, hey, my R1s cancel here, my R2s cancel there, and the parallel resistance is R1, R2, the product, divided by R1 plus R2, the sum. And a lot of times people learn this equation and think that that's a universal equation, but it's not. What condition has to be true for this to be correct? For 2 parallel resistors. If you were to use 3 resistors, it would have turned out to be R1, R2 plus R2, R3 plus R3, R1, all divided by R1 plus R2 plus R3. Is that right? No. It'd be R1, R2, R3, all divided by R1, R2 plus R2, R3 plus R3, R1. Okay, it's more complicated. And so I do 3 so people realize that the equation I put in the box is a special case that only works if you have 2. Now, when you're adding them in series, of course, it's trivial. 2, 3, 4, 5. They just keep adding up. So those are equations for adding resistors in series and parallel. And you had experience with that in lab this week. So one of the fun jobs that we give students in a class like this is to take some complex arrangement of resistors and say, okay, what's the equivalent resistance? And so to analyze this, you look for sets of resistors that are either in series or in parallel. And this is already analyzed for us, unfortunately. Some people might have said, I think that R2 is in series with R6. Why is that incorrect? I mean, I could have rewritten that piece as I could have written it like this. You say, well, R2 and R6 are one right after the other, so why wouldn't that be in series?
You've got 2 sets of parallels, and one has 3 resistors and the other has 2, so that each of them.
That is true, but the key here is, if they're in series, there has to be no alternate pathway for current. It has to be anything that goes through the first one has no choice but to go through the second. And with this arrangement, I could have current that goes through this one, come down and go through that one. It didn't have to go through R2.
So if R5 was not there and it was just going to R6, then would it be so valid to say that R2 was in series with R6?
It would not, because I could also have current do that. Right? It's an option. Not an expected outcome, but it's an option. It's a possibility. So it's still not in series.
You're saying you can have current go through R2 and go back through R3?
Yeah.
Is that really possible?
Is it really possible? Yeah, electrons can do it. It's not the expected outcome, but it's possible. And to be in series, it can't be. It has to be not possible.
But wouldn't that be flowing against the current?
Yeah.
Okay.
But it's still possible. Or to put it another way, the way you're thinking, Chad, is if I only had one resistor here, if it was like this. Okay, I'm just going to rewrite it. I'm just going to write 2 and 1. If it's like this, current going like that is going to merge to go through here, right? And so the current that goes through here could have come from here or here. And for them to be in series, there has to be only one option. That's 2 options. So you take these and break them up. As they've done, you have those 3 that are in parallel, so you combine them and replace them with one equivalent resistor. You have the 2 that are in parallel. You combine them, replace them with one equivalent resistor. And then when you reanalyze, you see, hey, these 2 are now in series. So then you combine those 2 in series. Why are R1 and R7 not in series here? Because there's another option. I combine these in series, and then these are in parallel, and then I have these in series. And after a total of 1, 2, 3, 4, 5 calculations, I end up with an equivalent resistance. We give you those things so you have practice with identifying what's series, identifying what's parallel, and using the rules. Are there practical applications? Oh, there are so many circuits out there that yes, there are. Can I think of one? No. All I can think of are contrived problems for physics class. But it's so you have practice using those equations. Now we have something that's a real problem. Well, real problem. I have a 12-volt battery. I have a 1 ohm resistor, a 6 ohm resistor, a 13 ohm resistor. And I want you to tell me what the total current is that battery is using and what the voltage across those 2 parallel resistors are. How do you solve this based on what you know right now if you have not taken circuits class?
I assume you try to first identify which ones can be combined.
That's right. You start and you say what can be combined and what can be combined.
R2 and R3 should be able to be combined into one resistor.
So using the equation for adding 2 resistors in parallel, I have an equivalent resistance that I called R23 that's equal to 6.00 ohms times 13.0 ohms divided by 6 plus 13 is 19.0 ohms. And so I have that equivalent resistance. Now that I have that equivalent resistance, which 6 times 13 is 69 or 78. 78 divided by 19. Since 19 is a prime number, I don't know. Anybody? It's what? 4.7? Oh, okay. You're guessing. Yeah. That's good thinking.
4.1 will be bad.
4.1?
Yeah, that's the 6 times 13 divided by 19.
Okay, so we have 41 or 4.1 ohms for that. Now I can redraw my circuit, and I have.
Sorry, that should be 4.11. Technically.
Okay. 12.0 volts. 1.00 ohms. 4.11 ohms. How do I find the current now? Ohm's law says I is equal to V over R. The voltage difference going from here to here is clearly 12 volts. So that means I have 12 volts over that series combination. We can all add that series combination in our heads, right? Okay. I've lost some. And so that's a little bit more than 2 amps. 2.35. Okay, so I have 2.35 amps. And now that I know that current, what's the voltage across this? It's 1 ohm. It has 2.35 amps through it, so voltage is current times resistance. So that had better be 2.35 volts. And then for the other one, I could go and use the same thing, take 4.11 times 2.35, or I can just say, I went up 12 volts, I went down 2.35 volts, how much more am I going to have to go down?
9.65 volts.
And you see that equation is written here. Now that equation technically comes from a law that we will learn within the next 4 minutes. It's pretty obvious, hence they just throw it here before we've even seen it. The other way to do it would have been and it should give you the same answer. Okay, so what are these rules? I'm going to skip over this slide. In fact, as you can tell by the fact of what's said, I didn't intend to leave that one there either. Circuits that are neither series nor parallel need a more complicated analysis. This complicated analysis we will be doing in lab on Tuesday, the Kirchhoffs Laws lab. So today I'm going to teach you what the laws are, and then we'll practice doing those laws in lab on Tuesday. You'll have some textbook problems in between, just basic ones on the laws. But to do this, since the resistors are neither series nor parallel, you can't do it the way we did the previous problem. It won't work. And so we have to use 2 rules. First one, Kirchhoff's current law, known as KCL. There are other names for it. It's also known as the node law or the junction law. What does your textbook call it in your electric class, engineering students? Junction rule? Okay. Has different names. What it is the sum of the currents at a node equals 0. Well, you have to define node for that to carry any meaning whatsoever. Node technically means any place where 2 elements join together. So technically, and notice this is technically, if I have 2 resistors like this, there's a node between them. But that's a pretty ridiculous node, because if they're in series, we already said they have to have the same current. Kirchhoff's current law says the total current at the node is 0, or the current in equals the current out. Well, that's just repeating what we already knew. So nobody applies the node law to just 2 resistors that are tied together. Instead, we use what's called an essential node. An essential node is where we have 3 or more that come together. So when we use Kirchhoff's current law, we look at each essential node, and we can apply Kirchhoff's current law saying the sum of the currents at that node is equal to 0, which is the same as saying the sum of the currents that come into that node is equal to the sum of the currents that leave it. Now, what's special about this law? I tell you that Kirchhoff is an absolute genius because he took something that everybody knew, that was self-evident, And he named it a law, and now he's famous for it. Because all this says is, charge can't be made or destroyed, so if charge comes in, it's going to have to leave if you're not storing it. So an assumption of circuits is that you're not storing charge anywhere. Now you might right now say, wait a minute, we just talked about capacitors, and they store what? They store charge separation. The net charge in the capacitor was still 0 because you had plus Q on one side and minus Q on the other. So in our circuits, a fundamental assumption is nothing is storing charge. And so Kirchhoff's current law is simply stating charge is conserved, can't be created or destroyed. Which brings us to, I guess, where we'll end with this question, which is, what law is Kirchhoff's current law a restatement of? Read the question. Okay. We had 5 people who clearly weren't listening. Because I just said less than a minute before the question. It was simply a statement of conservation of charge. Okay, I'll see y'all on Monday. Have a great weekend. Unless there's a snow day.